Hello everyone. I am C.A. Morales from the Hangzhou International Innovation Institute of Beihang University in Hangzhou, China. In this talk, I'll discuss a joint work with Bautista from the Universidad Nacional de Colombia and Wuqiu Jung from the Chungnam National University in Daejeon, South Korea. The work is titled Characterizing Expansivity through C algebras. Our main goal is to show how the algebra of continuous observables, denoted C of x, can be used to characterize expansive homeomorphisms. This gives a purely C algebraic viewpoint on expansivity in dynamical systems. Part 1. Outline. The presentation is organized as follows. I'll begin with the motivation and some background on the link between dynamics and C algebras. Then I'll introduce the notions of expansive and strongly expansive observables. After that, I'll present our main theorems and their algebraic consequences. Finally, I'll discuss examples, non-existence results, and open questions that arise from this framework. Part 2. Motivation. Expansivity is one of the central concepts in topological dynamics. Roughly speaking, a homeomorphism is expansive if points that start close eventually separate under iteration. Traditionally, this is expressed in metric terms. There exists a small positive number, say, epsilon, such that if 2 points remain within that distance for all forward and backward iterates, then the points must be identical. However, metrics are external structures, while the algebra C of x of continuous complex-valued functions is intrinsic to the topology of the space. Our question is whether we can detect expansivity directly from this algebra, that is, by studying how observables separate orbits. Part 3. C dynamical background. The natural algebraic object associated to a homeomorphism F, from X to itself, is the C dynamical system formed by the pair C of X and alpha, where alpha acts on observables by composition with the inverse of F. This map alpha encodes how observables evolve under the dynamics. Each element of C of X can be interpreted as a measurement on X. So instead of looking at points and distances, we look at how these observables behave along orbits. In this setting, expansivity will correspond to the ability of observables to distinguish distinct orbits through their level sets. Part 4. Strongly expansive observables. Part 5. We begin with the stronger notion. An observable is said to be strongly expansive if there exists a positive number epsilon, such that whenever the difference between the values of the observable along two orbits stays smaller than epsilon for all integer iterates, the observable must take the same value at those two starting points. This mirrors classical expansivity, but acts at the level of observables rather than points. We denote the collection of such observables by sex P of F. It forms a subset of the expansive observables, which we define next. Expansive observables. Part 6. Structure of expansive observables. An observable is expansive if there exists a positive number delta, called expansivity constant, such that whenever the orbits of 2 points stay delta close for all iterates, then the observable takes the same value at those 2 points. The key theorem says that a homeomorphism is expansive if and only if every observable is expansive with a common expansivity constant. So, expansivity of F can be reformulated as a uniform separation property of all observables in the algebra C of X. In this way, exp of F, our second main result, describes the structure of the algebra of expansive observables, denoted exp of F. First, exp of F is an F-sigma subalgebra of C of X. This means it can be expressed as a countable union of closed subsets in the uniform norm topology. Second, it lies between the constants and the whole algebra. It equals the constant functions if F is equicontinuous and X is connected, and it equals all of C of X if F is expansive. Third, this algebra exp of F is invariant under topological conjugacy. That means two conjugate homeomorphisms share isomorphic algebras of expansive observables. It becomes a conjugacy invariant algebraic signature of the dynamics. Part 7. Consequences. One immediate application concerns periodic points. We prove that for any expansive observable, the set of periodic points of F intersects at most countably many level sets of that observable. From this, we derive that every expansive homeomorphism of a compact metric space has at most countably many periodic points. This is a well-known fact in classical dynamics, but here it follows from purely algebraic reasoning within the C framework. Part 8. Equicontinuous case. Equicontinuous case. In the opposite extreme, when f is equicontinuous, every expansive observable must be locally constant. In particular, if x is connected, the only expansive observables are the constant ones. Then, we obtain a C algebraic proof of the well-known fact that on infinite connected spaces, there is no homeomorphism which is expansive and equicontinuous simultaneously. This aligns with our intuition. In equicontinuous systems, all orbits move coherently, so no observable can separate points in a non-trivial way. Hence, within this framework, expansivity and equicontinuity appear as two algebraically opposite situations. Part 9. Pseudo-expansivity. Motivated by this dichotomy, we introduce pseudo-expansive homeomorphisms. A homeomorphism is pseudo-expansive if the algebra of expansive observables is dense in C of X. By the Stone-Weierstrass theorem, this means that expansive observables separate points of the space. We can arrange these notions in a hierarchy. Strongly pseudo-expansive implies expansive, which implies pseudo-expansive, and that in turn implies pointwise expansive. A natural question is whether any of these implications can be reversed. For example, does pseudo-expansive imply expansive? The answer is not known. Part 10. Theorem 3. Non-existence. Our third theorem gives a striking non-existence result. There is no pseudo-expansive homeomorphism of the circle or of the closed interval. Consequently, there are no expansive homeomorphisms on these one-dimensional spaces. This agrees with classical results, but here the proof uses only algebraic arguments inside C of X. Thus, the C algebraic viewpoint not only reproduces known dynamical restrictions, but explains them in purely functional analytic terms. Part 11. Summary. Let me summarize the main contributions. First, we introduce the algebra of expansive observables, exp of f, as a new invariant of topological dynamics. Second, we showed that the expansivity of f can be detected from the structure of this algebra alone. Third, we proved that exp of f is an f-sigma subalgebra invariant under topological conjugacy. Fourth, we gave algebraic proofs of two classical results: the countability of periodic points and the non-existence of expansive homeomorphisms on the circle and the interval. Altogether, this work shows that dynamical complexity can be expressed directly through the C algebra of observables. Part 12. Open directions. There are several open directions. First, we would like to know whether the extreme cases, exp of f equal to C of X or equal to the constants, actually characterize expansivity and equicontinuity. Second, the notion of pseudo-expansivity deserves further exploration. Can we classify such systems? Third, it would be natural to extend these ideas to non-commutative C algebras and to group actions beyond the integers. Finally, it would be interesting to clarify the connections with strict observability and fiber-wise expansivity, which appear in related works by other authors. Part 13. Thank you. Thank you for watching. I hope this talk has shown how C algebraic methods can illuminate classical dynamical notions, such as expansivity. Questions and comments are very welcome.